This is Syed Reshma Sharif. In this video lecture today I am going to give explanation about waveguides and resonators, that is in microwave engineering. First of all, introduction. Microwaves. Microwaves are same as electromagnetic waves. Microwaves are electromagnetic waves. Okay, whose range is from 1 gigahertz to 1000 gigahertz. Microwaves are electromagnetic waves and their frequency ranges from 1 gigahertz to 1000 gigahertz. For comparison, the signal from an AM radio station, AM here nothing but amplitude modulation. Okay, AM radio station that is of 1 megahertz, and signal from FM, FM is nothing but frequency modulation. Radio station is of 100 megahertz. Okay, signal from AM radio station is 1 megahertz and signal from frequency modulation radio station is 100 megahertz. Microwaves are so called since they are defined in terms of their wavelengths. Based upon their wavelengths only, isn't it? How their waves are, we are going to refer. Micro means very small. It means very small. Micro means. The micro refers to tininess. Tininess is nothing but very small. Tininess referring to a wavelength and period of a cycle of centimeter wave. Okay, of centimeter wave. For one centimeter, how many number of cycles they are moving? Okay, per centimeter. The period of cycle that is defined completely by microwaves. Okay. In other words, the wavelength lambda is a wavelength of centimeter waves. CM waves are nothing but centimeter waves. Yet microwave frequencies are very short, typically from few tens of centimeters to a fraction of a millimeters. Okay, few tens of centimeters to a fraction of millimeter. It means microwaves are very fraction of seconds. They are the wavelength of centimeter waves for one wavelength. Okay, 1 centimeter. In short, a microwave is a signal that has wavelength of 1 foot or less. That is, wavelength lambda is less than 30.5 centimeters. 30.5 centimeters is similar nothing but 1 foot. Okay, lambda is equal to C by F. Whereas to find frequency, here F is equal to C by lambda. Okay, here C is nothing but 3 into 10 power of 8. Okay, by 30 centimeters they given. Now we are converting this one into meters. What we will get 30.5 into 10 square. Okay, that equal to 984 megahertz. That is equal to 984 is nearly to 1000, isn't it? So we are writing 1 gigahertz. Okay. Here C is nothing but a speed of light in vacuum. By lambda is nothing but wavelength. We will get 1 gigahertz its frequency. So all frequencies above approximately 1000 megahertz is equal to 1 gigahertz. To about 1000 gigahertz are microwave frequencies. All frequencies which are above 1000 gigahertz, that is 1000 megahertz to about 1000 gigahertz, are called as microwave frequencies. Okay, so here this is of a microwave frequency or not? Yes, it is a microwave frequency. It is of 1 gigahertz. The higher frequency edges of microwave borders on infrared and visible light regions or spectrum. Okay, the higher frequency edges of microwave borders are on infrared rays and visible light regions or spectrum. Microwave frequencies are classified separately from light region, separately from radio waves. Okay, here these are microwave frequencies are classified separately from radio waves. Okay, radio waves are not same as microwaves. Okay, microwaves are little different. shows the various availability of electromagnetic frequency spectrum. Let us discuss this one. Okay, these are our microwave band L, S, C, X, K, U, K, K, A. Okay, L band, that is of frequency 1 gigahertz. Here 1 gigahertz, 2 gigahertz, and S band frequencies of 2 gigahertz to 4 gigahertz, and C band, X band. Here the frequencies of 8 gigahertz. This is of 12 gigahertz to 18 gigahertz, that is KU frequency band, and 18 gigahertz to 27 gigahertz, that is of K band. Here 27 gigahertz to 40 gigahertz, that is of Ka band. Whereas here 40 gigahertz to here, that is millimeter, and here the sub millimeter. Okay, 0.300 terahertz. Okay, here this one all are of ELF, SLF, VLF, LF, MF, HF, VHF, UHF. All are those bands. SHF, EHF, infrared, light, X-rays, gamma rays, cosmic rays, etc. Here the full form of these frequencies are ELF means extreme low frequencies. Okay, extreme low frequency. Here extreme low frequency, that is of 300 Hz. Here 30 Hz to 300 Hz. SLF means super low frequency. Okay. SLF, VLF means very low frequency, LF means low frequency, MF means medium frequency, HF means high frequency, VHF means very high frequency, UHF means ultra high frequency, SHF means super high frequency, EHF means extremely high frequency, infrared, light, X-rays, gamma rays, cosmic rays. All those rays cannot be visible to our naked eye. Okay, only some X-rays, and we can't see, isn't it? X-rays and all we will experience in hospitals, etc. But we can't see all those X-rays. They have the capability to penetrate into any region. Okay, the visible light is above infrared region and falls between 430 megahertz to 1 pHz. This region includes the fiber optics laser region. This is region above 1 pHz, includes X-rays, gamma rays, and cosmic rays. These cannot be visible to our naked eye. The various metric prefix such as mega, micro are given in table. This is a preferred table where all our frequencies given in power of 10. Okay, power of 10 and symbol. Extra frequency means power of 10 power of 18 symbol. We have to learn all those table, isn't it? We have to learn all these table. Here peta means 10 power of 15. Extra means in the power of 10 means we have to remember 10 power of 18. Like that we will remember. Symbol is E. Peta means 10 power of 15. Symbol is P. Tera means 10 power of 12. Symbol is T. Prefix means power of 10. Symbol is its symbol. Prefix power of 10 here. See, this is a symbol. Now here we are giving giga, 10 power of 9. Here G is a symbol. Whereas mega, 10 power of 6, M. Symbol is M. Kilo means 10 power of 3, K. Milli means 10 power of minus 3, M. Micro means 10 power of minus 6, mu. M, small m. Okay. Nano. Okay, no, sorry. Micro means this one. Mu. This can be called as a mu. Okay, nano means n. It is a 10 power of minus 9. Pico means 10 power of minus 12 p. Femto means 10 power of minus 15 f. Atto means 10 power of minus 18 a. These all table we have to remember. Carefully we have to learn all those. Okay, all the symbols and their prefix as well as the power of 10 values. Microwave region and band designations. Now, till now, what we will learn what are all the frequencies, symbols, how all those been in their ranges. Now we are going to discuss about microwave region and band designations. Microwave region is the electromagnetic spectrum is shown in table 1. Here the CCIR term. Here microwave region is electromagnetic spectrum. It is shown in table 1 along this frequency. As per CCIR, here nothing but Consultative Committee for International Radio. What is the full form of this one? Consultative Committee for International Radio. You have to remember what is the full form of this one. Consultative Committee for International Radio. These recommendations, it may be noted that beginning of each band is multiple of 10 of previous bands or the next bands. Okay. What is this refers to? Here in this table, see here the multiples of for each and every frequencies. It is of multiple or doubles the band. Okay, here 300, here 3 kHz, here 30, here 300. Okay, it means multiples for every band of frequencies. It has been multiplied. Here see 1 gigahertz, 2 gigahertz. Here 2 to 4. Here 4, 8, 8, 6, 8, 12. Here 18. Okay. Here multiples of 2. 1, 2 square, 4, 4 square, 8, 8 square, 8. Here are 2. Here 4. Again we are going to add till here. Here 12. Here again 4 we are adding. Like see multiples like that we are getting. Standard band designations for microwave listed as per Institute of Electronic Engineering. Institute of Electrical and Electronic Engineering is the industry standard. This is shown in our next. Let us see. Here band designations given as band designations, frequencies in hertz, applications. Here extremely low frequency ELF, that is 30 to 300 hertz. In this what we will get communication with submarines. This is mostly used underwater. It means these extremely low frequencies has the capability to penetrate into the water. Voice frequencies 300 to 3000 hertz. Telephone, baseband applications, etc. Telephone in our daily lives, I think everyone know about telephone, isn't it? Here this frequency we are going to use for this voice frequencies, that is 30 to 3000 hertz. Here next one is very low frequencies, 3 to 30 kilohertz. These are used in long distance point to point communications. Very rarely used, while I think these are used in sending messages from one destination to other destinations, while mostly these are used in military appliances, etc. Next one, low frequencies. Low frequencies are of about 30 to 300 kilohertz. These are used in point to point marine communications, time standard and frequency broadcast. Marine communication means they have the capability and point to point from one point to another point. Okay, it must have known low frequencies, isn't it? It must be known a designation. Okay, at the time it can use for point to point communication at marine. Medium frequencies 300 to 3000 kilohertz. These are used in broadcasting and marine communications. Okay, high frequencies 3 to 30 megahertz. These are used in moderate and long distance communication in all types. For example, aeroplanes. Okay, planes, and all we can use this mode of communication. High frequencies, very high frequencies, these are used in television, FM service, navigation, and police. Okay, ultra high frequencies, these are of 300 to 3000 megahertz, that is 3 gigahertz. These are used in short distance communication, including radars. Radars means radio detection and its ranging. It ranging when ultra high frequencies are used at short distance communication, including radar. Whenever the distance is very less, at the time these ultra high frequencies are used. We can find radars also. Super high frequency, that is 3 to 30 gigahertz. These are used in radar, microwaves, and space communication. Very, very important communication. Space communication. Okay. Satellite launching, how the satellite is moving, and all we can. What is the place of the satellite? What are all the activities going on? And we can find through these super high frequencies. Next one, extreme high frequencies. That is 30 to 300 gigahertz. Same as this one, radar, microwave, as well as space communication. Radar communications are nothing but radio frequency, and it's a ranging. Okay, radio detection capability, very tiny waves. Okay, this can have capability to move in extreme vacuum also. The different microwave regions based designs and corresponding services of electromagnetic waves are shown in this above table. Okay, now band designs and frequencies. The standard band designs for microwave frequencies listed IEEE as shown in figure. I think everyone feels that these are boring, but we have to learn all those values, because unless and until if we won't learn all those values, we can't able to detect. These are mostly helped in our in communication department. Whenever you move in communication field, you have to learn about all those. Being an electronic students, we have to learn all those frequencies and their bands also. Okay, first UHF frequency, that ranges from 0.3 to 3.0. Large frequencies 1.1 to 1.7 gigahertz. All those are in gigahertz. See, similarly here, S band, C band, X band, KU band, K band, KA band, Q band, U band, M band, E band, F band, G band, R band, some millimeters. Sub-millimeters are above greater than 330 gigahertz. Okay, the standard band designs of micro frequencies are listed based upon the IEEE format. Okay, IEEE has shown this table. Advantages of microwaves. There are some unique advantages of microwaves over lower frequencies. Increased bandwidth availability, improved directive properties, fading effect and reliability, power requirements, and transparency properties of microwaves. Transparency properties of microwaves. Increased bandwidth availability means if we know the particular frequency, if we know about particular frequencies, then the bandwidth availability we also know, because so many number of bands were increased. So it is a good thing for us. Improved directive properties. Okay, directive properties means ultra high frequencies they are using, microwaves they are using. So these can be improves properties of our works. Okay, fading effect and reliability. It cannot have a fading effects, and the reliability is more. It means correct information we will get. Power requirements are very less. Transparency properties of microwaves. Next one, first of all, applications of microwaves. Now let us discuss about what are all the applications of microwaves. Microwaves have broad range of applications in modern technology. Now we are living in present modern technology, isn't it? They are most widely used in long distance communications, radar, navigations, radios. Our relatives are in foreign countries. We can able to communicate with them or not. All those can be used for long distance communications, radars, navigation. For where without knowing any address we can move by using Google Maps and all those are used with these microwaves. First one is telecommunication. Microwave frequencies are used in communication such as telephones, TV, space communication, earth to space and space to earth, telemetry communication links for railways, etc. Here, telecommunications. Telecommunication means for us everyday broadcasting of TV programs such as telephones. We can make a call with any. Okay, space communication means from lecture today I am going to discuss about TM waves as well as TE waves. Previously, we found we got two equations, that is of TM waves as well as TE waves. Now I am finding the values of Ez and Hz by using a Maxwell's wave equation. What is Maxwell's wave equation? We are having terms Ex, Ey, Ez and Hx, Hz, Hy, Hz. Now what we are going to find? We are going to find these two only. These Ex, Ey, Hx, Xy we are going to find by using Maxwell wave equations. Okay, let us see how this Maxwell wave equations be. Now we know del value. Maxwell's wave equation. Maxwell's wave equation states that is del cross H is equal to J omega epsilon E. Okay, this is our Maxwell wave equation. Now del is nothing but dou by dou x of I bar plus dou by of y j bar plus dou by dou z of k bar. Whereas h is equal to hx I bar plus hy j bar plus hz k bar. Similarly, E is equal to Ex I bar Ey j bar plus E2 k bar. This Maxwell, this problem is very important. Okay, in this chapter don't left this problem. This is compulsory. You have I think 4 or 5 problems in this chapter. Okay, if you cover all these 4 chapters, 4 problems in this chapter, you will definitely attempt any question given from this chapter. Okay, now let us see with Maxwell wave equation. Del cross H is equal to J omega epsilon E. We know the value of E. E is equal to Ex I bar plus Ey j bar plus Ez k bar. Now I am writing expanding this term del into del cross H. That is nothing but del cross H is nothing but I bar j bar k bar, whereas del value dou by dou x, j value dou by dou y, k value dou by dou z, whereas h value here hx, hy, hz is equal to j omega epsilon E value Ex I bar plus Ey j bar plus Ez k bar. Okay, replacing dou by dou z as r. R is an operator. Okay, dou by dou z is equal to minus r, an operator. What we will get, let us substitute in this equation. Okay, let us replace this equation. What we will get? I bar j bar k bar dou by dou x dou by dou y minus r hx hy hz is equal to j omega epsilon I bar Ex plus j bar Ey plus k bar Ez. Okay, now I am Now multiplying these, equating these two terms, that is I into dou hx, I into dou by dou hx by dou y minus r hz. Okay, dou by dou y of hz, dou by dou y of hz plus dou by plus hy into r minus j bar dou by dou x, these two terms, this one, this one, this one, this one, crossly we have to multiply and then subtract. What we will get? Dou by dou x of hz minus this one and this one, r into hx. Here minus r into a minus of minus, it becomes plus. Plus r into hx, then plus k, this one, and dou by dou x of hy minus dou by dou y of hx is equal to j omega epsilon I bar ex plus j bar ey plus k bar ez. Now equating these two terms, what we will get? We will get, see, now I am equating this one and this one, again this one and this one, and this one and this one. Let us see the values are. Equating all the quotients. Okay, what we will get? Dou h z by dou y plus hy r is equal to j omega epsilon ex. J omega epsilon ex. Next one, d by dx hz plus r into hx is equal to ey. J omega epsilon ey. Dou by dou x of hz plus r hx is equal to j omega epsilon ey. Next one, dou by dou x of hy plus, here minus, sorry, here minus dou by dou y of h x is equal to j omega epsilon ez. These three are of equation 3, 4 and 5. Okay, I am arranging all this. Okay. Now, similarly from Maxwell's second equation we have second equation. What we have? We have del cross E is equal to minus j omega mu h. In previously j omega epsilon h, here del cross E is equal to minus j omega mu h. Okay. Here we are equating these two terms. Similarly, in previously what we did, like that only. I bar, j bar, k bar. Here dou by dou x, dou by dou y, dou by dou z. X Ey Ez is equal to minus j omega mu h. Here we are substituting dou by dou z as minus r. What we will get? I bar, j bar, k bar, dou by dou x, dou by dou y minus r, ex, ey, ez is equal to minus j omega mu h. Now expanding these equations, what we will get? Now I am expanding this one, okay. What we will get? Minus j omega mu I, whereas h value? I bar hx plus j bar hy plus k bar hz. Now similarly in previously here like that we have to expand this term also. I into dy by dy of Ez minus into minus plus r into ey. For j here d by dx of Ez minus into minus plus r into ex, we will get plus minus dou by dou y of ex. Now equating all those terms. Similarly like this only we will get. Let us see after equating all those terms what we will get from Maxwell's second equation. Expanding I bar, j bar and k bar. Okay, dou E z by dou y plus r ey is equal to minus j omega mu hx, dou by dou x of Ez plus r into ex is equal to j omega mu hy, dou by dou x of ey minus dou by dou y of ex is equal to minus j mu hz. These all are equation 6, 7, 8. Okay. Now combining equation 3, 6, what we will get? Equation this one and this one. Okay. Now what we will get? Now I am combining these two equations. What I will get? Let us see. Combining equation 3 and equation 6. Now what we will get? This one and this one. Hy is equal to r into, let us see fully we will solve, dou hz by dou y plus hyr by hyr is equal to j omega epsilon ex. Okay. Now my equation 3 and equation 6, dou Ez by dou y plus r ey is equal to minus j omega mu hx. Now after combining, what we will get? Hy and hx. For eliminating hy only, we get ex from equation 7. Okay, then hy from equation 7 we will get hy, near hy hy is equal to, okay, hy is equal to 1 by j omega mu. 1 by j omega, hy is equal to 1 by j omega mu, okay, into dou by dou x of Ez. For this value, I am sending all those terms here in this side. What we will get like this. Okay. Mu plus r into Ex r by r into Ex by j omega mu Ex, okay, is equal to j omega Ex, okay. For getting this hy value, we are sending all those terms this side, okay. We get this hy value. Hy value is equal to 1 by j omega mu dx by d by dx of Ez into r into Ex by j omega mu, okay. Now Ex is Ex of substituting this hy value in equation 3, this one, in this equation hy value we get, okay. We are substituting in this equation. What we will get? We are substituting hy value in equation 3. What we will get? Dou h z by dou y plus hy value how much? 1 by j omega mu dou by dou x of Ez plus r into Ex by j omega mu into r is equal to j omega epsilon Ex. Substituting hy value in equation 3. Now what I will get? Here dou hz by dou y plus 1 by j omega mu dou by dou x of Ez plus into r plus r square, r into r square Ex by j omega mu is equal to j omega epsilon Ex. Okay, I am sending this term this side, okay. What we will get? Ex common, okay. I am sending this term that side. Ex is common. J omega epsilon minus this one, it will move here. What will be r square by j omega mu is equal to r by j dou x plus r square Ex by j omega mu, okay. We will get or not? Now multiplying these two equations, we will get Ex j omega epsilon minus multiplying this term with j omega mu. What we will get? Ex j omega mu by j omega mu t minus r square is equal to R. Here j omega mu and j omega mu get cancelled. Dou Ez by dou x plus r square ex. Here j omega mu dou h by dou y. Okay, now next step. Ex minus omega square mu t mu epsilon minus r square is equal to r dou Ez by dou x plus j omega mu dhz by dy. Ex minus is common, minus I am taking omega square mu e plus r square is equal to r dou Ez by dou x plus j omega mu dou h by hz by dou y, where r square plus omega square mu t is equal to h square. Now dividing this equation, dividing this term with dividing this term with minus h square. Here minus h square throughout we get what we will get? We will get r ex is equal to, sending all those terms this side, okay, is equal to minus r by h square into dou ex Ez by dou x minus j omega mu dou hz by dou y, equation 9. Okay, similarly Ey is equal to minus r by h square dou Ez by dou y plus j omega mu by h square dou hz by dou x, equation number 10. Ex is equal to like this and Ey is equal to like this, whereas hx is equal to minus r by h square dou hz by dou x plus j omega epsilon by h square dou Ez by dou y, equation number 11. And hy is equal to minus r by h square dou hz by dou y plus j omega epsilon by h square dou Ez by dou x. This is equation number 12. These equations are given a general relationship for field components. All these equations give general relationship between the field components within a waveguide. See here what we all discussed, we are equating here we found two equations. Okay, here Maxwell first equation, from Maxwell second equation we will get all the six equations. Now we are comparing third and sixth equations. Then what we will get, combining these two equations, dou h by dou y h y r is equal to j omega epsilon ex, and equating this third and sixth equation. This one is of equation number 6. Dou z ez by dou y plus r into ey is equal to minus j omega mu hx. Now we are eliminating hy. Only we will get ex term from equation number 7. Now in this term we are placing only hz. We are eliminating all remaining terms. We will get hy. Here for finding this equation, we are eliminating hy. Okay, and we will get ex value from this equation. Now from this seventh equation we are eliminating this hy value, and what we will get, we are sending all those terms, we are removing this one, we will get only ex value. Okay, we are removing this term. Then hy is equal to 1 by j omega mu plus 1 by j omega mu ex. Okay, is equal to hy value. This one only we are writing here. Okay, now substituting hy value in this equation. In which equation? Equation number 3. Substituting this one in this equation, what we will get, dou by dou y of hz plus hy value how much? 1 by j omega mu dou by dou x of ez plus r ex by j omega mu in this equation. What we will get is equal to j omega e epsilon ex. Then dou hz by dou y plus 1 by j omega mu dou by dou x of ez into r plus r into r square ex by j omega mu is equal to j omega epsilon ex. Now ex, here for getting ex I am sending all those terms here. What we will get, ex is equal to 1 by j omega epsilon. We will get all the terms if we send this side. Okay, by multiplying this equation by j omega mu, we will get j omega mu, here denominator and j omega mu get cancelled, and the remaining term we will get this one. Ex is ex of minus omega square mu epsilon is minus r square is equal to r dou by dou x of ez plus j omega mu dou h by dou y. And from this term we are commonly taking minus, and for finding this value, in previously we get this value as we consider this value as h square. We are placing this in this term, ex of h square is equal to r dou ez by dou x plus j omega mu dou hz by dou y. Okay, dividing this term with h square, what we will get, this one is of h square, this with h square we have to divide. Now I will get the term minus r. I am sending all those terms in this side. Okay, then what we will get, minus r by h square dou ez by dou x minus j omega mu dou hz by dou y. Okay, here similarly ey, for ex this value, for ey value how much, minus r h square dou ez by dou y. Here only x, in y only, here dou y is changed. Okay, same value here we will get for hz by dou x. Okay, electrical field here dou y, whereas in magnet field that is in x value. Then we find hx value. Hx is nothing but minus r by h square dou hz by dou x plus j omega epsilon by h square dou ez by dou y. Okay, here for electric field, here the values, here the h values we will get. So for in magnetic field, that is h value, here we will get E value. That is only the difference between these two. General equation for this field of components within a waveguide. Okay, by seeing this equation, don't get fear. These are all very simple steps. If you from starting onwards, if you correctly do all the steps, it will make very easy to learn. Okay, thank you for watching. If you have any doubts regarding this, please comment me on my comment section. Microwave engineering topic, waveguides. Okay, first of all, in waveguides, a frequency is higher than a frequency is higher than 3 gigahertz. Here, for this 3 gigahertz, the electromagnetic waves along the transmission lines, these are all the transmission lines. Okay, here the electromagnetic waves, we are sending electromagnetic waves, isn't it? In this transmission lines or cables, it becomes very difficult, mainly due to the occurrence of both in a solid dielectric needed to support the conductor. In the conductor themselves, in these conductor themselves only, it must be a solid dielectric, a solid dielectric medium must be needed. Okay, to support the frequencies to transmit. Okay, next, a metallic tube. This is a metallic tube which can be used to transmit electromagnetic waves with all frequencies. Whatever kind of frequencies, this metallic tube can be used for different frequencies. A hollow metallic tube of uniform cross section, the hollow metallic tube of uniform cross section, same cross section, but must be used transmitting waves, successive reflections from the inner walls. Successive reflections from inner walls, these transmission tubes must be used. Any shape of cross section of waveguides can support electromagnetic waves. But since irregular shapes are different to analyze, the rarely used rectangular, circular waveguides are become more common. Okay, here mainly we are going to discuss all this topic about waveguides and how for more number of frequencies how it must be needed. For different frequencies, circular waveguides commonly they are used. Now, how the propagation of waves in rectangular waveguides. Now, propagation. Propagation of waves in rectangular waveguides. Okay, now we are going to discuss in previously what we discussed, mainly rectangular as well as the square waveguides are used. Okay, here rectangular waves are situated in a rectangular coordinate system with its breadth on x-axis along with y-axis, and the wave is assumed to propagate along z direction. Let us see with a small diagram. This one is of x-axis, this one is of y-axis. Okay, a rectangular wave. Now I am taking a rectangular waveguide. Okay, a rectangular waveguide which is situated with both x and y-axis. Okay, whereas a waves that is propagate at z direction. Propagated at z direction. Okay, the distance between these 2 points is nothing but b, that is width. This one here at a point, this one is of its breadth. Okay, length into breadth, isn't it, in rectangle? here this is air. This one is Z, direction of propagation. Okay, this one is of rectangular waveguide which is located on both x and y axis. Here the B is the point, the width of distance between these two is B. Here breadth, the distance between this one is A. Okay, the air inside it, Z is the direction of propagation of a wave. Now the wave equation of transverse wave equation of both transverse electrical waves and transverse magnetic waves. The wave equation for this one is given by delta square Hz for transverse electric waves. Okay, transverse electric waves. Whereas delta square E is transverse electrical waves. Okay, transverse electrical waves. Now we are going to discuss a wave equation for these two. Now del square Hz is equal to minus omega square mu epsilon Hz. For transverse waves, transverse electrical waves, Ez is equal to 0. Whereas in transverse magnetic field, in transverse electrical field, Ez is equal to 0. Whereas del square Ez is equal to minus omega square mu epsilon Hz. For TM waves, Hz is equal to 0. Okay, whereas epsilon is permittivity or availability of stored electrical energy in electrical field, whereas mu is permeability that is 4 pi into 10 power of minus 7 n by a square. For magnetic field, the electric field is 0. For electrical field, the magnetic field is 0. Now deriving the equation, and now exploding delta square del square Ez in rectangular coordinate. Okay, now here we are having all x-axis, y-axis and z-axis, isn't it? Now all our delta square Ez, it is in three forms. Okay, dou square Ex by dou x square plus dou square Ez by dou y square plus dou square z by dou z square is equal to minus omega square mu E is equation 1. Okay, this is of equation 1. Now I am equating this electrical field. Okay, for this electrical field in rectangular coordinate. This one is our equation. Now this equation is of 1. Now the wave propagation in z direction operates as in this z direction. In this z direction, the wave propagation, how z direction is dou square by dou z square is equal to r square, where r is nothing but here a constant. Okay, we have this r square in this z direction. We have to substitute this one in equation 1. Now dou square ex by dou x square plus dou square ez by dou y square plus dou square ey by dou z square plus dou square dou by dou z of, it means we have to write r square into z term we have to write like this. Okay, is equal to this one minus omega square mu epsilon ez. Now we have to send all those terms here. What we will get? Now the equation is dou square ex by dou x square plus dou square ey by dou y square plus r square ez plus, I'm sending all those terms here, omega square mu epsilon ez is equal to 0. Here in this both term ez is common. Now dou square ex by dou x square plus dou square ey by dou y square plus ez common r square plus omega square mu epsilon is equal to 0. This term is of constant. Okay, remember this equation 1, and this one is of equation 2. I'm writing both equations here. I'm erasing all those terms. Okay, let us see. This is of equation 1 and equation. This one is of r square plus omega square mu epsilon is of constant. Then r square plus omega square mu epsilon, that can be written as h square because this term is constant. Now I am substituting this term in this equation. Okay, what we will get? Let us see. Dou square ez by dou x square plus dou square ey by dou y square plus h square we are substituting in this term. What we will get? H square ez is equal to 0. Okay, now here h square ez is equal to 0 for TM waves, for transmitting transverse magnetic waves. Okay, here if we substitute Ez is equal to Hz, what we will get? We will get transverse electron. Here dou square Ex by dou x square plus dou square Ey by dou y square plus H square Ez is equal to 0, whereas this one here TM waves, whereas Hz is equal to 0. This term is equal to, this is for transmission of magnetic waves. Whereas dou square is similarly same equation we will get as a electrical field also. Dou square Ez by dou x square plus dou square Ey by dou y square plus H square Hz is equal to 0 for transverse electrical waves. Okay. By solving the above partial differentiation equation, we will get solution for Ez and Hz using Maxwell equation. By using Maxwell equation, let us discuss in next video. Thank you for your watching. If you have any doubts regarding this, please comment me on my comment section.